Hello everyone! We're going to take a look at the Unit 2 study guide. It is Friday, October 2nd, and we're working here during IC. So in order to be working along with me, you're going to need a calculator and you're going to need a periodic table. Now, I do have some students in my room right now who are taking their quiz retake, and the last day to do so will be on Monday. That would be Monday, October 5th. So, but anyway, right now what we're going to do is we're going to take a look at selected questions, and because I do have quiz takers in my room, I kind of have to be careful about the ones that I decide to show you. Okay? So this first one that we're going to look at is question number 1. And a lot of students, when I was walking around, I kind of realized that maybe they might be doing this one wrong. So we're going to actually take a look at this one at closer detail. So we'll do this one first. Okay. I don't know if you guys remember a conversation that I had. I'm pretty sure each class I talked about this. I had a student who actually took the mass of a proton and the mass of the neutron and looked that up, and that's how they were calculating their average atomic mass on one of the homework assignments that I gave you for average atomic mass. So with that in mind, I decided that was actually a really good teaching moment for everybody, and that's what I want you guys to do for number 1. So on this very first isotope, what we're going to do is actually use the real masses of a proton and neutron to help us get the mass of the isotope. Alright, so on this first isotope, what we're going to do is we're going to take 82 and multiply it by the real mass of a proton. And the real mass of a proton is 1.007276 AMU, and that'll give us the mass of a proton. But remember, in the nucleus we also have these neutrons, so I'm going to take 122 and I'm going to multiply it by the real mass of the neutron, right here, is 1.008664 AMU. Alright, so let the calculator do all the work for you, and I'm going to share with you what I got. Okay, for this first isotope, the total mass, I got 205.65364. Can anyone in the room confirm that for me? Yeah, is that what you got? Thank you very much. Alright, so there's our first isotope, and you would continue to go through and do this for each isotope that you've got. So I'm going to do the second one over here. Second one, I got 207.670968. Can anyone confirm that for me? Great. Keep it rolling. I'm on the third one. Okay, on this guy, on the third one, I got 208.679632. Am I good? Great. Last one. Okay, on the last one here, I got 209.688296. Anybody confirm? Yeah? Awesome. Okay, so we got all of our masses. Whew, that was a lot of work. What we're going to do now is we're going to actually solve for the average atomic mass, because all you need for average atomic mass is the mass and percent, and you see that the percents were actually given to you. So on this first isotope, let's get this rolling. We're going to take that percent, 1.37, divide it by 100, and times it by the mass of the isotope. The exact mass was 205.65364. Put a plus sign in between. Let's do that second one. 26.26% divided by 100 times the mass of that second one was 207.670968, close parentheses, plus sign. Let me move over a little. This one is 20.82% divided by 100 times 208.679632, and that last one, 51.55% divided by 100 times, running out of room again, hold on, 209.688296. There it all is. Alright, take your time punching this in on your calculator, okay? Don't want to make any stupid mistakes. Make sure you use your parentheses. This will take me a while. Make sure you do plus signs in between your parentheses. Oh boy. Okay, moment of truth. I hope I'm right, 208.893267? Is that what you got? Oh, you're still trying it? Yeah. Is that really what you got? Seriously, too? No way. Nice! I got it on my first try. Okay, everyone. Now let's talk a little bit about sig figs. Sig figs do not come from percents, they come from mass. So the only masses that you really had, if you look at the original problem, the only masses that we had actually came from the mass of the protons and neutrons. So we're going to look at those. 1, 2, 3, 4, 5, 6, 7. So protons have 7 sig figs. 3, 4, 5, 6, 7. And the neutrons also have 7 sig figs. So we're going to round to 7. 4, 5, 6, 7. Check that 2. Do you need to round it up? Yes. So it's going to be 208.8933, and the unit here is atomic mass units. That's my alarm. Hold on. Hey, since we're studying for our tests and stuff like that, we're going to keep rolling. Okay, now that everyone is done with their quiz retakes in the room, we can actually look at this problem. This was the chart at the very beginning of your study guide. Alright, so I'm going to review just a few concepts with you. Alright, when you're looking at the periodic table and you look at an element, say for example like carbon, kind of looks like this, 12.00, or I'm sorry, not 00, it's actually 12.011. Okay, this number right here is your atomic number. This atomic number also equals the number of protons. This right here we call your atomic mass. Not your mass number, but atomic mass. I apologize for my pen, it's just not working very good when I zoom up like this, so yeah, it is what it is. But the number of protons is also in a neutral element. You know, an element doesn't have any charges, at least not yet to you guys. But this is also going to be equal to the number of electrons. And you guys remember that there's isotopes, right? What if I had, for example, carbon-12, carbon-12, and then I also had another isotope, carbon-14. Let me kind of refresh your memory. These numbers right here are what we like to call the mass number. And the thing that you have to remember about the mass number is that technically a mass number is equal to the number of protons plus the number of neutrons. Alright, there's a big difference between atomic mass and mass number. Mass number is counted by like a whole number, and it's just the protons plus the neutrons. So be careful. What you've got up here, up on the top in this little chart, is you've got isotopes. So I don't want you necessarily looking for, when you try to get the mass number, I don't want you looking at the periodic table's atomic mass. That's not how you get mass number. Okay, so to refresh your memory, this is going to be equal to the addition between your protons and your neutrons. You add those together to get your mass number. number of electrons is going to be the same as your number of protons. So let me choose a different color here. Electrons will be the same as the number of protons. And then your atomic number will also be the same as the number of protons. So those three columns right here should all be the same in red. The one that I marked in red, those will all be the identical. And then for mass number, you just have to add your protons and neutrons. Alright, which piece of information is going to help you to figure out what the element is? The atomic number. The atomic number is the same as the number of protons. Those two areas right there identify what the element is, and that's the atomic number. Alright, just give me 1 second. Alright, so let's just do a real quick example. I'm just going to do one of them, okay? If the atomic number of this first one is 9, that means the protons will be 9, and the electrons will be 9 as well. The mass number on this guy comes from adding the protons and neutrons together. So I'm going to take the 9 and I'm going to add 10. That's 19. Now if you look at the periodic table, you're looking for the element that has an atomic number of 9. And that element would be fluorine. And the symbol for fluorine is a capital F. Alright. Now the next little table here, we're looking for the charge and the mass of these various particles. So let's have a quick recap. Protons are positive, they're located in the nucleus. They have a relative mass of about 1 AMU. 1 atomic mass unit, AMU. Ugh, my pen is sucking really bad. Anyway, neutrons. Neutrons are neutral, and they're also located in the nucleus, so they have 0 charge, and their mass is about the same, about 1 AMU. And I don't know if you knew this, but if you look at question number 1, the one that we already did in the video, like way up here, if you look at question number 1, they actually tell you the specific mass, and if that's what you want to use on there, that's perfectly fine. Alright, but the electron. Electrons are those tiny, tiny little guys that zip around the outside of the nucleus. And it would take roughly 2,000 of these guys to equal the mass of a single proton. If you want to get really specific, the mass here would actually be a fraction of an AMU. So you see I've got my numerator is a 1, and the denominator, remember how I said it's about 2,000 of them? Sorry, I'm trying to get that number there. It's actually 1,840 of these would equal the mass of a single proton. So you see how I set it up as a fraction? If you actually punch it in on your calculator, you can if you want. It would be 1 divided by 1,840. And whatever that number is, that's what you can enter as well. It would be in the form of a decimal. Alrighty. Okay, so we did the chart up here. We also did question number 1. Let's look at question number 2. Which subatomic particle identifies an atom as that particular element? Maybe some of you guys forgot, or maybe you've never heard of this word subatomic. Subatomic particles are the particles that build an atom. So what particles, what tiny little guys, actually, when you throw them together, they can make an atom? Quick answer, protons, neutrons, and electrons. So protons, neutrons, and electrons are subatomic particles. Alright, so which one of those will tell you the identity of the element? Protons, you got it. Okay. Question number 3 is another average atomic mass problem. I hope you're getting good at these. Alright. It says that copper has 2 isotopes. Copper 63, and it gives you a percent, and it gives you a mass, a very specific mass. So whenever this specific mass right here is given to you in any of these average atomic mass problems, definitely use these rather than just the mass number. These right here, these are called mass numbers, okay? But if they ever give you these, I want you to use these instead, okay? Alright, so let's set it up. Your first isotope has an abundance of 69.2%. Take that percent divided by 100 and times it by the mass, the specific mass. 62.930 AMU. There's my first isotope. Add. The next isotope has an abundance of 30.8%. Change that to a decimal by dividing by 100, and then multiply by 64.928 AMU. Alright, grab your calculators. Use your parentheses. All right, on my calculator I get 63.54534. Can anyone confirm that for me in here? Is that what you got? Nice, thank you. Okay, on this problem we don't want to take our sig figs from the percents. Okay, percent abundances are not where we get our sig figs from. We want to look at the masses, okay? So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. We should have 5. 1, 2, 3, 4, 5. Check that last one to see if you need a round up. The 5 does not need a round up because the guy next to him is a 3. So this is 63.545, and the unit here is AMU, atomic mass units. Final answer. Okay, we're zooming right along. Now what we need to do is the isotopic symbols of that question for the isotopes that we just did. Alright, so just remember how to do isotopic symbols. It's really easy. What you need to do is get the symbol of the atom. Copper is the symbol of the atom, and you had two isotopes. One of them was isotope copper 63, and the other one was copper isotope 65. Those numbers are mass numbers. The way it works is you put the mass number up high on the left side, like this, and then you put the atomic number below that. And so you just probably check your periodic table. Copper's atomic number is 29. And there you go, you just leave it like this. Done. Alright. Number 5. Why is an element electrically neutral? What that means is that why do they have no charge? That actually comes back to one of these problems that we just did. Do you guys remember how the number of protons is equal to the number of electrons? Protons have a positive charge. Electrons have a negative charge, right? So the number of protons equals the number of electrons, and that's why an atom is neutral. Protons equals electrons. Question number 6. How can there be thousands of different types of atoms when there's only about 100 different elements on the periodic table? Specifically, there's 118 elements. How can we have thousands of different types of atoms out there? Isotopes, that's right. They're the same atom, but a different number of neutrons, and so they have a different mass. Okay. Number 7. What is the difference between the mass number and atomic number? Oh, that vocab, we got to be really careful. Remember, mass number is when you take the protons and you add the neutrons. That's mass number, and it's a whole number. Atomic mass is the mass when you look at the periodic table. That's the mass that you see down underneath the symbol, and it's usually in the form of a decimal. And that comes from an average of the isotopes. So it's a big difference. Mass number, protons plus neutrons. Atomic number, that would be the average of all the different isotopes. And it's got decimals. Okay. Number 8, and I'm so glad that you guys are watching this video because you can see number 8 in color. On your guys's, it's not in color. I'm so sorry. Color really does help. So let's see if this makes a little bit more sense now that you guys can see it in color. You need to identify them as a substance or a mixture, and then after that, tell me if it's an element or compound, homogeneous or heterogeneous. Okay, this guy right here, the first picture, it looks like we have two different things in there. We've got these red things and we've got these blue things. But can I ask you one question? Is everything in the box identical to itself? Did they all look the same? All those particles, they look the same. Each one of them has two blues and one red. So it's all identical. Therefore, it cannot be a mixture. If there's two different things in there, then that would be a mixture because there's two different things inside of it. So this is not a mixture. This is a pure substance. Next question. Are these elements or compounds? Now, if it's an element, they would have to be identical particles connected together. But you see, I have two different things. I have blue and I've got red. That makes it a compound. These are compounds. So in box A, this is a pure substance compound. Let's look at box B real quick. Is everything in box B identical? Well, we got this one particle over here. We've got like two of these red ones, and the other one is two reds and one green. So you see how there's two different things inside of that box? You now have a mixture. Question. Is that mixture fairly uniform, or do you see a cluster or a grouping or layers of material? I don't know, it seems pretty well mixed. I'm calling that a homogeneous mixture. Alright, we're running out of time, folks. I hope this has helped you out just a little bit. We will be making another vodcast later. Have a great weekend, everybody.